Okay,
Yeah, it's like 50.
we are getting to the time when introductions happen. And it's my great delight to introduce our speaker for the Sheepy Pie Memorial Lecture today. And I will just tell you a little bit about this lecture series. It started, I think, in the 90s, if I remember correctly, Jim. It says so over here that the first Sheepy Pie lecture was 1995, and it has been going since then thanks to the Sheepy Pie family who have supported it and made contributions to the endowment. And it's a great pleasure to do this in memory of Sheepy Pie, who lived from 1913 to 1996 and served on the faculty of the University of Maryland at College Park starting in 1949. And I believe it was called the Institute for Fluid Dynamics and Applied Mathematics at that time. And IFDAM and the Institute for Molecular Physics, which was housed in the squat little building right next to the Physical Sciences Complex. The Institute for Fluid Dynamics and Applied Math and the Institute for Molecular Physics or Science got combined in 1976, I believe, to become the Institute for Physical Science and Technology. And Dr. Pie was actually a fluid dynamicist and mechanical and aerospace engineer. So it is particularly appropriate to have someone representing those disciplines today. And Professor Pie's many contributions included books, articles, students, colleagues who carry on his memory and so on. And we have had a long tradition of interdisciplinary talks here that combine the interests of different departments. So these talks, the Sheepy Pie lectures, go right across the boundaries of engineering, mathematics, science, biology, chemistry. All of these disciplines are part of the sequence of talks that we have had. And it is really a great pleasure to welcome Professor Naomi Leonard from Mechanical and Aerospace Engineering at Princeton University today. She's the chair of the department and Edmund S. Wilson professor over there. And what is particularly attractive and interesting to me is that she is no stranger to the University of Maryland at College Park. So after graduating from Princeton, this is where she came to pursue her graduate studies. And she happened to be a student in the same building where my office has been for the last 25 years, the A.B. Williams building. And she was a student with Professor Krishna. And Krishna has actually arranged a whole day of activities for her tomorrow. So I think some of you over here will actually be spending time with Professor Leonard tomorrow. But she got her master's and PhD over here in electrical engineering and went on to do many things. She is a MacArthur Fellow, a member of the American Academy of Arts and Sciences, a fellow of the ASME, IEEE, IFAC, SciEd, a lot of different races. And the most recent award, I believe, may not, but the one I have listed here is the 2023 IEEE Control Systems Award and the 2024 Richard E. Bellman Control Heritage Award. So those are some of the most recent recognitions. And, it's a delight to have you here, Professor Leonard, and I look forward to your talk, which has a very interesting topic, if I can find it. It is flexible decision making. Okay, it's up there. I hard to read it from pieces of paper rather than look at screens. And so it's my great pleasure to welcome you. Thank you so much for coming and spending time with us and getting to know some of the newer faculty in different departments and being here to tell us about this topic, which I believe you will put in a political context.
Not today.
Thank you.
Thank you very much. Thank you. So it's a great honor to be here and a great pleasure. It's really a nice, wonderful homecoming for me. So I'm going to talk today about what we call the fast and flexible decision-making that's needed for a group, or we sometimes call them multi-agent systems, to successfully manage the uncertainty, the variability, the dynamic change encountered when functioning or operating in the real world. And I'll make precise what I mean by fast and what I mean by flexible, and I'll present a modeling framework for studying fast and flexible decision-making, how systems manage to be responsive and to be robust in changing contexts. So this framework can be used to study the natural world, but also can be used in design, which is an interest of mine as well. And this work builds on a history of prior work, and it's closely related to a number of well-established literatures, including the literature on consensus dynamics and the various extensions and variations on collective animal behavior and on computational neuroscience models of decision-making. So I wanted to start with this video. I mean, I've been studying animal groups and for about 25 years, and I never get tired of this. This is a group, this video is taken by researchers in Rome. This is probably more than 1,000 starlings moving together in the presence of a falcon. So what's sort of incredibly striking is that there's no leader, and yet the birds move so quickly in response to the predator, and at the same time they seem to be impervious to what must be an enormous amount of unimportant fluctuations and uncertainty. Moreover, these kinds of remarkable displays of fast and flexible decision-making in the wild don't depend on whether agents agree or disagree. So this isn't about consensus decision-making, this is about collective decision-making. So here, for instance, whether to go left or right, you can see that they've come to some kind of decision individually, and nobody's actually going in the same direction. So one of the critical features of group decision-making is breaking indecision, which you see that these robots have not done. They're all programmed to go, they're trying to get across the room, and they didn't take into account what to do when they run into somebody, so they get stuck in this moment of deadlock. So indecision breaking is important to avoid deadlocks and collisions, which can be costly in an enormous number of contexts. And the problem is actually a challenging one. So how do we design, how do animal groups, how does the brain deal with the possibility of indecision? And it can be challenging, in particular when there's little evidence to lead you to understand which of options is the one to take. So here, I'm sort of showing you an illustration of the model in use that I'm going to present for you today. So here you can see that these little robots that are still trying to get around the room or trying to get somewhere will quickly, collectively decide. This is actually pairwise. They're deciding whether to go left or right, but sometimes they'll go left, sometimes they go right. They just need to make sure to break the indecision and make one of the choices. So I just wanted to also show you a couple of the particular stories in the literature about animal groups that have served, because I've studied them, but they've also served as kind of some of the bricks that I built this formulation on that I'm going to talk to you about today. And the first one is this example of animals moving in the plane together, like the school of fish in this paper by Cousin et al. From 2011, where they're moving in the plane, and there are half of them have been trained to be interested or to know about one of these sort of sources of food, and the other half, the other source of food. And Cousin et al. Wrote a paper in 2005, and you're looking at a result from that paper. So this was a simulation study of that very problem. And the idea is that what happens is, this is a heat map which is showing you the high likelihood direction on all the different simulations they ran as a function of the angle between these two targets. So when they're far away and they can't really distinguish, they kind of split the difference. So they don't make a decision, they're in this state of indecision, they're just going straight, but at some point the angle gets big enough and they can distinguish, and then they become mutually exclusive and they make a choice for one or the other. But here, the group is not splitting, they're either going one way or the other, which is pretty incredible. And I think what I want you to notice is that this sort of this decision-making from indecision to a decision is fast, right? You see, it's a steep curve. And the other example I wanted to talk about, which was also very inspirational for me, is the story of how a group, a swarm of honeybees makes a decision when they are choosing among nest sites. So this is a very well understood story, how this group of individuals that never makes any kind of comparison among the individual sites can extremely effectively pick the best of N when they have scouted out a bunch of sites. And so this is data from a paper by Tom Seeley and co-authors from 2006. And what you're looking at in the top plot is the activity of the bees over time as they scout out different sites. There are 5 sites in this particular experiment. The second plot, the middle plot, is their activity in doing the waggle dance, which is what you see in the photo, which is the way that a bee who's scouted out a site advertises this site to the other bees that are watching it. And the bottom is what's called the piping signal, which is an indicator that a quorum has made a decision, and they come back and they make a decision and say, hey, we've made a decision. But what's interesting is you see there's this accumulation of evidence, and then boom, we get this very fast decision that gets made in a nonlinear way. I got very interested in this when I saw this paper by Tom Seeley and his colleagues. They were studying the problem. They had put for the bees 2 candidate nest sites of equal quality. What do? Do they do what we do in the supermarket? Which one should I choose? No, of course they don't do that. And so they were able to hypothesize that they used this additional signal called stop signaling. It's kind of like the shut up signal, because what happens is when one bee is dancing who's committed to one site, an observer who's committed to another site will headbutt that dancer. I mean, it's amazing. I mean, it's just actually spectacular because it tempers the dance and it allows them to essentially flip a coin. And so we studied this. They had developed a mean field model to study this, and what you're looking at on the right is from a paper where we basically proved that there was this pitchfork bifurcation. So what you're looking at is the steady state as a function of the rate of this stop signaling. So we could show, sort of extending what they did in their experiment, that we could sort of predict that there was a critical value. If the stop signaling was below it, they would stay half and half, half for site A and half for site B. But then after that critical value, so here blue points refer to stable equilibrium, red to unstable, and the line going at 0.5 becomes unstable when there's enough of this stop signaling. So this was a sort of a beautiful story that, it all makes sense in retrospect. There you see sort of empirical evidence of a pitchfork bifurcation. It makes perfect sense when there's a symmetry that you're going to see something like a pitchfork. So this framework that we've developed that I'm going to tell you about was done in collaboration with Anastasia Bizieva, who's my former PhD student. She's now assistant professor at Cornell, and Alessio Franchi, who is a longtime collaborator who's at the University of Liège in Belgium. Oh, that's great. Okay. see? I can't see it.
No?
I can use the mouse.
use your-
I'll use the mouse. So what we, why is it not working? Oh, that one, okay. So what we've done is define this notion of fast to be breaking of indecision as fast as it needs to be, as fast as indecision becomes costly. And by fast, I mean that we're not just going somewhere else, we're actually exponentially, diverging very quickly away from indecision. So it's sort of not just a sort of a passive, making a decision, it's actively destabilizing indecision or neutral and becoming then stabilized at another equilibrium which corresponds to a decision. And by flexible, I mean this ability to be responsive to signals that are important to successful functioning or operation, even if they're weak or rare, without compromising the ability to be robust to unimportant fluctuations. Right? That's another kind of thing that you wonder, how in the world do they do that? So this is what we're trying to understand about the natural world so that we can abstract out, ask more questions about the natural world, and then also think about how we would use this in design. So flexibility in our thinking refers to what we call tunable sensitivity to inputs or to stimuli or to even biases, internal biases. And that means that there should be parameters or dials in the dynamics of this process of decision-making that modulate the regimes in which the system will be ultra-sensitive, so responsive, and the regimes in which the system will be insensitive and robust, right? Because it's got to do that, and it should be tunable, because that needs to be tuned as a group or multi-agent system moves from one context to another, where things might be very calm, and then things might be very, switchy But all of this requires nonlinearity. It requires feedback to understand how this can happen, right? Negative feedback is what gives us robustness. Positive feedback is what gives us responsiveness. And in our thinking, we also need to have some analytic tractability. We have to understand these mechanisms and be able to say things, at least in certain kinds of cases, in an analytical way. So we set out to formulate this as follows. So we start with a set of N sub A agents, and we think about them having a sensing or a communication network. And so what I'm showing you here is the graph that describes that network. So every node is an agent, and these arrows describe who's communicating with whom. The AIK super A is the weight on these edges. So that's the information that the weight that the agent I is putting on the information that it's getting from agent K. We call this the adjacency matrix. It's just the matrix of all the AIKs. But they can be bidirectional, they can be one directional, and they can also be positive, those are the blue ones, and they can be negative, those are the red ones. We also have a set of options, so there can be lots of alternatives, so 5 nest sites or multiple directions to go in. So N sub O options, and we also consider a network among those. We call it, well, we don't call it, we're sort of stealing from social science literature, they call it a belief system network. So like those targets, when they're far away, you can imagine there's a positive edge. So if I'm for one, I'm for the other. And then as they move away, that edge weight would become negative and they become mutually exclusive. So if I'm for one, I'm not for the other. And so then the starting point is to think about opinion formation and decision-making as a dynamical process that can be described by the coupled evolution over time of these agents' decision states, which we define as follows. So one set is the set of opinions. So Zij here is a real valued variable, function of time, that is the agent I's opinion about option J. And so at time t here. And so the more positive it is, the more in favor agent I is of option J, the more negative, the more it disfavors option J. And when it's 0, it's in a state of indecision. It's neutral about that option. And we also introduce another important variable, which we call attention. So every agent has this attention variable, which also can be a function of time, U sub I. And actually, we implement it as essentially a gain on all the observations that the agent is making. So if you're not attending, then you'll have a low attention. If you're attending, then you'll have a high attention. There could be a network graph associated with that. So my attention could rise as a function of those who I can observe maybe becoming engaged in the decision-making process. So I let bold Z be the vector of all those opinion variables, and bold U be the vector of all those attention variables. And so then what I'm going to tell you is this story of how this process is controlled by feedback, negative and positive feedbacks. It's organized by bifurcation. So indecision, we're going to think of as being broken through a bifurcation. And it's modulated by network structure. And so this we bring our analytic tractability to, so we can say as much as we possibly can say about it and understand these sensitivities and understand tunable sensitivity. I did want to, before I show you the model, I just want to mention, so I'm going to do a sort of a model-based study, but I wanted to mention that the model actually derives from so-called model-independent approach. So here the idea is that a model-independent approach relies solely on empirically verifiable assumptions to make testable predictions. And so any model or real-world system that verifies or maybe only weakly violates those assumptions should inherit some ground truths. And so here one assumption is that opinions evolve continuously in time according to a smooth dynamical system. Another is that opinion formation is a network phenomenon in the sense of Golubotsky and Stewart. And so one can use symmetries, one can use equivariant bifurcation theory and prove these ground truths for model building. And so this idea that one ground truth follows that if all the agents are indistinguishable and all the options are indistinguishable, so you have kind of maximal amount of symmetry, then it should be that a transition from consensus, where everybody is exactly agreeing, to dissensus should be possible merely by modulating sort of the extent by which individuals are cooperative or not, right? There shouldn't have to be some finely tuned network structure. It should be very facile that one can switch, because we see groups, fish going to one side, fish then splitting among, this is like a dissensus, and then this is a consensus. So the model I'm going to show you is essentially designed so that it derives from these principles, so it captures these ground truths, but then we can make it messy and mucky and introduce all kinds of heterogeneities and break all these symmetries, and we can see what's sort of left after we break all those symmetries, what can happen. So here's the model, and the model consists of the rate of change, DDT of ZIJs of all those opinions, and then the rate of change is the second equation of all those attention variables. So in the first equation, the first term is just a damping. It's just a linear damping kind of term. It's a negative feedback. If everything else is zero, it's just going to regulate me at neutral, right? There's no reason I have to make a decision. I should just do what I'm doing. This term BIJ, that's evidence, that's either internal bias or some kind of stimulus, or input, we'll call it input, BIJ, so that's evidence of, if it's positive, then it's evidence for agent I to be, to be in favor of option J, and if it's negative, it's evidence in opposite. Then we have this big positive feedback term, which is essentially just sort of the sum of all these things that we could potentially observe. One is just a kind of a self-reinforcing term. That's this first term. The second is the sum, this weighted sum by those edge weights in the graph of other agents' opinions about option J. The next one is sort of internal. That's agent I's opinions of other options and how that affects their opinion about option J. And then this is other agents' opinions about other options. So this is just sort of the complete, you might not have all this stuff, but this is sort of the complete rundown of everything you can have. And this is a positive feedback system. So these are driving you to be either more in favor or more in disfavor. And this is where attention comes in importantly. So this is a gain in front of all of that stuff, right? And so when attention's high, this is high, and what's interesting is this is the positive feedback. So when attention's high, positive feedback will dominate. When attention's low, negative feedback will dominate. And actually, when attention is at that critical value, that's where we're going to get our bifurcation point. S is just a sigmoidal function, like hyperbolic tangent, and that the idea here is that when the argument is small or moderate, it just gets treated as it is. But if all this input is, all this observations is coming in super in favor or super in disfavor, it's just getting capped. And so this is very much motivated from biophysical models of these kinds of things, but it also is essentially enough. This kind of nonlinearity is enough to see the plethora of things that can happen in collective decision making. In the second equation, tau, you could have a different time constant, so these kinds of could be happening at different time scales. I'm actually going to set tau u equal to 0 in the sequel, so ui will be equal to this basal value plus another feedback term. So ku is a feedback that's feeding back observations of an agent's own or other observations of opinions, and I don't even care, if it's what the opinion is. I just get engaged in a process because either I've got a little bit of input B and my opinion's starting to go up, so I see that something's going on, or I see some people in the back of the room stand up suddenly, and I think, oh my God, something's going on. Before I decide or I even notice which door they're going out, maybe there's an emergency, I get involved at least in the decision-making process. So this is actually an additional positive feedback that's important, right? So let me just sort of show you this. This is kind of what it would look like sort of from a control theoretic point of view. We've got these B's, the inputs coming in. Here's our opinion state. We got the damping, the negative feedback. We got the positive feedback from all the terms of observation, outcomes, this decision, but then we also have this additional positive feedback on this attention variable, which is modulating the positive feedback. So that's how we get really fast decisions with this positive feedback when it gets triggered. So I think it's helpful before I then dig into the theories, just sort of show you what happens, right? Because this will illustrate all the kinds of things that can happen. And what I'm showing you here is a setup. So I have 13 agents, and this is what the graph looks like. And so these are the bidirectional edges, and they're making decisions about two mutually exclusive options. So I only need to plot for you ZI1, the opinion of every agent I about option 1, because if it's mutually exclusive, it's positive if it's for option 1, and it'll be negative if it's for option 2. And what I'm going to do here is introduce some input of magnitude B bar. So the same magnitude to these 4 agents, but 2 of them, the blue ones, are in favor of option 1, so positive, and negative if they're in favor of option 2, just to these other 2. All the weights on this network are just +1. This is the exact same story, except that the weights on the network are -1. And just to give you sort of a preview of what's to come, because we can predict this, the size of these circles reflect the sensitivity of the individual nodes, the relative sensitivity of the nodes to this input. And so I'm going to apply this input just for this period of time. It's like from 0.7 to 0.8 units of time. So I turn it on, I turn it off. The only difference between these two plots is that I use B bar as 0.1 and I use B bar as 0.3. And so what I'm going to show you here is that this is an illustration of this implicit threshold. It's it's based on this distributed input. Because this is what happens when I apply this model. I've introduced actually randomness. There's randomness in all the parameters. I've added some noise, random initial conditions, and you can see that this is below threshold, right? So nothing really happens. But here a ton happens, right? Because it's nonlinear, we get these very fast formation of opinion. Here, all the edges are positive, so everybody is kind of in agreement of being in favor of option 1. Actually, because these two dots are larger, it's option 1 and not option 2. And here they split the difference, even though all the edges are negative, they split the difference. Some go for option 1, some go for option 2. It perseveres, right? So that it doesn't go away after we turn off the input because we have multi-stability, right? So now this is a stable equilibrium. It's all robust to all that, albeit small uncertainty and variability, randomness that I injected. Also interesting because of the network, even those are getting here, the input for option 2 are joining the group and making this decision. So what's happening, the model can be explained by what I've introduced as an indecision breaking bifurcation. So just by way of review, a local bifurcation is a change in the number and stability of steady state solutions. And so this picture here is a bifurcation diagram. And so what I'm showing you here is a plot of the steady state values of this variable y, which you can think of as kind of, I'll tell you more later, but it's a scalar, sort of just think about it as a lumped variable that represents the opinion of the group. And I'm showing you that as a function of the basal attention U0. So that's our bifurcation parameter in this picture. And when y, the opinion is 0, the group is in a state of indecision. That's the neutral state. But you can see this is actually a subcritical pitchfork bifurcation, just because I've cranked up that feedback in the attention dynamics case of U. So I get the subcritical bifurcation, so I actually get these two saddle bifurcations. So this, we can prove all of the story. And these two decisions, so neutral becomes unstable at this critical value of basal attention. When a basal attention is greater, it becomes unstable, and we get these two decision states. So this is for, I'll call this decision state 1 and this decision state 2. So here y is positive and here y is negative, but we get all sorts of interesting things. We get tri-stability here, we get bistability here. So if I were to start these are just two different initial conditions, near neutral in this regime here, U0 is less than U0 star, everything just converges to neutral, to indecision. But if if U0 is greater than U0 star, I get big decisions forming, and they're forming quickly. But there's randomness. So, if I start or noise pushes me on this side, I'll make the decision here. If noise or I start below, I'll go this way, right? So it's sort of, I'm flipping a coin depending upon which side I'm on. And so here's kind of a robotic illustration of this. So what I'm showing you here is a robot that's trying to get across the room, and a person is coming straight at them. Okay, so there's no evidence for this robot to decide whether to go left or right. And the variable z, I just have a scalar opinion for this robot, and it's sort of, has to do with like the larger it is positive, the more actually positive is to go to the left, and negative is to go to the right. So it's just going to move at a straight, constant velocity forward. And this is just going to tell it how much it's going to diverge from a nominal controller that's just trying to get it across the room. And so this is what happens with these dynamics. Sometimes it goes to the left, sometimes it goes to the right. Okay. What's key here is that we're actively destabilizing the indecision. So it's breaking a decision, it's just making a choice, right, which is really important. So that's indecision breaking, so we know very well what happens when you introduce a little bit of asymmetry. Here, I'm just taking that input B, and I should also say that this is also some kind of lumped variable, which I'll explain to you in a moment, but it represents our distributed input across this network. So stimulus could be coming in where we have this whole vector of inputs. But now I'm making it even a little bit positive. We know how the pitchfork bifurcation unfolds, and it looks like this. So super interesting. Those same initial conditions that before gave us neutral now give us both of them. There's only one stable equilibrium here. And they're going to diverge quickly, sort of like the ghost of that singular point, that bifurcation is going to push them away really fast. And this is an exponentially stable equilibrium, and they're going to be attracted very fast. And so you can see this, we call it ultrasensitivity, right? We have, you think about, for control theorists, the input-output map essentially blowing up at that singularity, so we get really fast response. And what's interesting is, as B gets bigger, that picture, expands, and this point moves backwards. So for larger B, we could have had a smaller U naught and still gotten a decision. So this is kind of a preview that this basal attention is a tuning parameter. It tunes the threshold. Like this is the threshold. Like for this value of B, if U naught were here, I make a decision. But if U naught were here, I'd be stuck. That's why we saw for the smaller value of B, we saw nothing, and the larger value of B, we saw this big cascade. And everything is symmetric if B is evidence, a little bit of evidence, tiny little bit of evidence for the other option, right? Those same initial conditions will just go the other way. And so here's again this same robot. So what we've done at the beginning, we gave it a little bias. Okay, it's in the US, it's going to go right, but this person, maybe they're from the UK and they move to the left. And so it has this super ultra sensitivity. So it can change its mind. It went to the right and then it quickly changed its mind so that it could avoid colliding. Broke deadlock and avoid colliding. And so another way to look at this idea of tunability, it's really important to think about the hysteresis that we get from multistability. So now I'm showing you these bifurcation plots. So again, this is our same Y, this sort of lumped opinion as a function of this lumped input. If we're way down here, this is just a linear kind of passive kind of system. The interesting places are right here, where we have this hysteresis. As U naught increases, the hysteresis gets smaller. But hysteresis is really nice here because we have a hysteresis between each decision state and the neutral. So we have one here and we have one here, and this is because of the multistability. This already gives us another kind of robustness, right? So small fluctuations and things going on aren't going to change the story, right? We're here and B gets a little smaller, gets a little bigger, nothing's going to happen until we get all the way over here and then jump down. And so here, this switch is from neutral to a decision state for the whole. This is for the whole network, right? This is a cascade that's happening with these arrows. And in this particular case, let's call the value of B here B1. We're just getting linear behavior here. We're not going anywhere here. We're getting a big jump here. And so I'd like to think about U naught as this tunable parameter, this tunable sensitivity to the input, and it's tuning us between like this ultra sensitivity and this robustness, right? Here we're robust to this input, and here we are super responsive to this input. So all of this we can rigorously prove and derive. So we prove this indecision breaking bifurcation in those high dimensional nonlinear dynamics. So again, U naught is our bifurcation parameter with its critical value, U naught star. So we prove conditions, for example, under which we have one simple zero eigenvalue at the linearization of these dynamics at this bifurcation point. And so the bifurcation manifold is one dimensional, and it's tangent to this critical subspace. So we do this analysis locally, right? So instead of trying to compute the whole manifold, we look locally and we essentially, can understand how the bifurcation happens if we focus in on this critical subspace. So I'll just call that critical subspace the span of a unit vector, we'll call it V. And so this thing that I was calling Y, the lumped value, is literally the projection of the vector of all these opinions onto this space where everything's happening. So this high dimensional space, but I have this bifurcation happening along this one dimensional space. So that's, and V itself, the components of V predicts the opinion configuration, who's got the highest opinion, who's got the next highest, who's got an opposite opinion if there are negative entries. Furthermore, there's also something we call the sensitivity space. So when we understand the unfolding, when this input comes in, it's triggered when there is enough of an alignment of this vector of this distributed input onto this sensitivity space, right? And furthermore, we can actually prove and derive expressions for the bifurcation point, the critical subspace, and the sensitivity subspace as a function of the adjacency matrix for those two different networks or their Kronecker product. So that's really something. You tell me, I mean, albeit this is, for a fixed network structure, but we can then tell you for your network structure what these spaces will be. But then it starts to get us thinking about, like, as network structure changes, what does that mean for how systems might be tuning what's happening. So we do this through this tool called the Lyapunov-Schmidt reduction, which is, I'm just sort of showing you for the example of N sub A agents making decisions about two mutually exclusive options. So I only have one opinion state for each agent. It turns out that we can prove that V is actually V max, which is the right eigenvector of the largest eigenvalue of these adjacency matrix when it's a simple real eigenvalue. And so we can prove things about the network structure. For example, if it's all positive edges and it's a connected graph, you'll get a largest simple real eigenvector, eigenvalue lambda max. So V max is our V. That's our critical, the span of V max is our critical subspace. And the left eigenvector of this leading eigenvalue is W max. That's the critical subspace. The sensitivity subspace. So Lyapunov-Schmidt reduction, for those of you who are familiar with it, just allows us to take this high dimensional dynamics and look at the eigenspace, the eigenspace associated with that zero eigenvalue of the Jacobian at the bifurcation point, and do this. We essentially do a Taylor series expansion of the projection onto that space. So in the case of the pitchfork bifurcation, it's just a one-dimensional space, and we're looking at the equation for the steady state solutions, and this is what, for this model here, this is what it looks like, where Y is this projection of Z onto V max. That's how we were able to derive where all the action is, and B is this projection of all the input onto W max, and U star is inversely related to this this maximum eigenvalue, lambda max, and then this form is isomorphic to the normal form for this subcritical pitchfork with this sort of quintic, the two saddle node bifurcations. Okay, so we do this, we can do this in spades. This is a really nice and tractable because we are looking locally, but that's kind of all we need because we're using feedback to stay near this, stay locally with the bifurcation point. So here's just an example, so just to kind of understand it in the case of just two agents with a positive edge, right? Here's the adjacency matrix. So eigenvalues of +1, -1. So the maximum is the +1. The corresponding eigenvector is our V. It's 1, 1, right? It's a span of 1, 1. And so sure enough, this is when U naught is greater than U naught star, we get our bifurcation. This is just the phase portrait. So this is agent 1's opinion about option 1. This is agent 2's opinion about option 1. And we see that the neutral becomes unstable and we get this pair of solutions. And this is decision state 1 when both agents are 4 in favor of option 1 and both agents, it could have gone the other way, both agents are for option 2. If we had a negative edge, here's, it's minus this, the 0, 1, 1, 0. So we have the same two eigenvalues, but now the corresponding eigenvector to the maximum eigenvalue of 1 is 1 minus 1. So that's our span. That's where all the action is. So now we have neutral as unstable, but decision 1 is agent 1 for option 1 and agent 2 for option 2. Agent 2 for option 1 and agent 1 for option 2. those are the two options. Like we saw in the picture, except we saw with more agents. And the story continues, right? If you have a Vmax that has all positive edges, you know, the Vmax, the components, like I said, will tell you for the two decision states, I mean, one will just be this flip of the other, you know, who's going to be more in favor, who's going to be less in favor. If you have negative edges and you end up with a Vmax that has mixed sign entries, who's going to be, you know, for one and who's going to be for the other, how they split. And this would be just the flip over the horizontal axis. I mean, we can even do it when we have a network of agents and a network on the options. You know, so then we look at the Kronecker product of all these things. And so we can, you know, use this network structure to predict. So this is all the agents splitting about option 1, some for, some against. And then this is agent 7, how it splits among the different options. So it's for some and it's disfavoring others. So this is what I mean by this all being modulated by the network structure. I mean, we can even do this when we don't have conditions that give us a single, but rather a pair of you know, zero real part eigenvalues, a very complex pair. And so then we don't prove a pitchfork, we prove a Hopf bifurcation. So this is an example, like you know, a ring with all negative edges. It gives you these perfect oscillations. And of course, we can predict all this. But it gets even more interesting when you, so this is the belief network among options. Here's 3 different interagent networks. And you know, you get all these different things, but because we have these network structures, we can predict the relative amplitudes and the relative phases based on the network structure. And then one other thing I want to point out is that, so everything I've been saying, so we just understood how Y is modulated by structure, but also the input, how distributed input gets introduced to trigger a system. And so the idea here is we actually don't just have ultrasensitivity, we have what's called selective ultrasensitivity, because it means, so if our vector of B's is well aligned, we'll get this triggering, but if it's misaligned, right, if it's orthogonal to, or even just transverse to, we might get nothing. Right? So this allows us to understand how even very small inputs, if they're well aligned, might trigger something, whereas even large ones that are misaligned might not. And it could be, you know, that the reason that, you know, fish can be responsive to predators, even if it's a rare occurrence, and then disregard spurious kinds of activity. It could be that this is the filtering, and it could be that, you know, edges are being changed depending upon the environment so that you can filter out in this very subtle way, right? So this idea that, you know, for well-aligned, you don't need as much magnitude in an input to get a cascade, right? And furthermore, like how these trade off is all tuned by this parameter U0, right? Like this border here, right? So again, modulated by network structure. So I already kind of mentioned this. I have a project now to look at this beautiful work by Andrew Hine and his group. He's now at Cornell. He's looking at these coral reef foraging fish in the wild and how they are able to basically, what he calls it, rejecting misinformation when there's these spurious escape response maneuvers, but they're distributed randomly across the group as opposed to maybe the alignment with the sensitivity space when there's a real threat maybe is exciting you know, a different set of individuals. So we're studying this and we're going to study it in the lab. Here's just a couple examples of what we're doing with in application. So I sort of showed you these ideas, but now we're thinking about multi-robot systems moving around multi-humans and how this kind of fast and flexible decision-making can make things work. I have a collaboration with my colleague Jaime Fizek, and this is work by his student who's really interested in how groups make split-second decisions. Here's just a single race car driver trying to make decisions about, split-second decisions about passing. So here there are 2 pairs of mutually exclusive options: pass or stay behind, pass on the right, pass on the left, and he's actually closed the loop with a neural network that's learning the parameters in our model the opinion dynamics are actually being used to tune weights. And then he does this kind of trajectory game optimization of paths, of trajectories. But he's run this, and he tells me that without this, he's using sort of black box approaches that just, with all this fancy learning, he said that this actually makes a huge difference. It just sort of cuts down on the possibility of things that can happen, and you can be much, more likely to have a successful pass than otherwise. Okay, so that's all sort of good stuff, but things can break, and one of the reasons that things can break is, I've sort of showed you this idea of like making a decision, right? But I haven't told you, what if you have to make another decision, right? I mean, I showed you the robot very quickly changing its mind, but that was at the beginning. What if it was really determined to go right, and then someone got in its path? And this is kind of what you see, and this is a simulation of this robot heading across the room, and now the person has gotten its way, and it knows to change its decision, but it's stuck up there, and then the bifurcation diagram flips, and it has to go a long way. And so what the idea is, like, how do we make this more agile? Well, think about what neurons do, right? They're excitable systems. You don't make a decision and then just stay there. You spike, and then you come back down, then you spike, and then you come back down. So what if we adopt that kind of idea? We make a decision, like we jump up here, and then we return back to the point of ultrasensitivity. So if we have to make it again, we'll be right there, right? But if we have to make the other one, we're at the ready, right? We just want to be at that ultrasensitive point to see if things will push us back. And we do this by adding a slow negative feedback to that expression for attention, right? So this makes the system excitable, and we call it spiking nonlinear opinion dynamics. So here's the equation where I've plugged in for U, and now I'm plugging in for U with this, just this slow negative feedback. Tau sub US should be at least an order of magnitude greater than tau sub Z, and this builds on a huge literature on from neuroscience, as well as a more recent literature on spiking control systems, Rudolf Spolker, and this whole kind of world of neuromorphic engineering, which I'm getting quite interested in. So this, our old picture of the block diagram, we have this now slow negative feedback that is now attenuating attention after everything has spiked. And so then this is what things look like in that case. On the left is the one you saw before, where it's getting stuck. But now we're going right, whoops, left. And it's sort of self-tuning. Like the frequency will speed up. It's this kind of, it's super agile. It's on demand. It's a event-based decision making. And it's also kind of it is a generalization of a unidirectional spike. So now in principle, we can generalize this to multiple options, and we can have a system that spikes in every direction for which we have an alternative option or strategy. So we can, we're in the process of sort of proving all this story. I mean, I'll just sort of show you that if you look at just for a single agent with these spiking dynamics, and you look at the intersection of the null line, so when z dot is equal to 0, that's the red, and US dot is equal to 0, that's the blue. On this phase portrait, you can prove you get this Hopf bifurcation, and you get these sustained oscillations in the presence of an input. So here B is positive, so we're going to the upper Hopf, but we'll get a Hopf in the lower, in this case of two mutually exclusive options. And then we can generalize to multi-agents. So this is just the model of multiple agents making decisions about two mutually exclusive options with this additional term. And so I'm just showing you a little example of three agents that have positive edges. I'm only giving input to one of them. We get this cascade of spiking when this B1 is turned on in the positive direction. I can also look at it for other networks. Here I have negative edges between all of them. And so agent one goes in the direction of its input. The other ones go in the opposite direction. And I just illustrate that in this example of now 3 robots are trying to get across the room, and there's 2 humans, those black arrows coming at them. So on the left, maybe they're carrying something, so they have a network that keeps them together, say, and you can see them, this sort of cascade of spikes, and you can kind of see it speeding up in frequency when the human got near them. And here, this is that example with the, some going one way and some going the other way. So maybe there's not enough room for all of them to fit. And so this negative edges make sense. Let's just split up somehow. And so you can see, agent, the blue one was going to the right. So I'm gonna sort of close just by telling you a couple of the other kind of exciting new directions. So among other things, we are thinking about this in a truly neuromorphic way. We're embedding these dynamics in soft robotics. So thinking about systems that need sort of self-tuning, spiking, like large magnitude and kind of self-tuned frequency. So here we've done it with, this is just a little Fitzhugh Nagumo oscillator that is allowing this inchworm-like robot, and this is just still in equation, so this is just, we haven't made it yet, but to move, and now we don't have to create a variable, we're using strain to essentially, as input to this circuit that creates a voltage that moves this thing along. I also wanted to mention that in case you're interested, I have a project, so I work with, this is a kinetic sculpture that I've created in collaboration with a bunch of people that is actually allowing me to explore these dynamics. In the case where we got those oscillations, so these are gently rotating robots that we have customized, and they're synchronized as they move. They move slowly. It's meant to be kind of a meditative space, but it's also a way to visualize and sonify, because I work with a composer and a lighting designer, the dynamics that you saw. So there's sort of anti-synchronization of actuators in the bases that create the oscillations, and then there is synchrony among the agents, right? So there's a website if you're interested to learn more. Final note that I'm engaged with Anastasia and Dan Garbonis. So Dan is a postdoc with Ian Cousin, and the 4 of us are looking, actually Dan and Anastasia are leading this effort to connect these decision-making models, in particular this mean field, this spatial decision-making model that Dan and Ian have been using to explore that original problem I showed you, that sort of spatial decision-making among targets. They're using an Ising spin type model where they look at like a network of they think about like the rate of change of neurons, a population of neurons, one for each of the options. And if you write down the mean field model for their Ising spin model, and you do a little bit of analysis, you can show rigorously how it maps onto our story, which I think is really important, right? Because there's so much work that's been done where we think about, these kind of probabilistic type models that we think about phase transitions and what that means, but to be able to actually map it so that we can really understand, what's going on, here's that angle, and now we understand where it shows up. It shows up in this, like I told you, the edge weight between the 2 options, and we can understand the dynamics that they've designed or they've derived for how theta ij changes as a function of the way that these fish are perceiving their environment. So we can go back and forth between these kinds of models in really exciting ways. I'm out of time, so thank you very much.
Thank you very much. We have time for questions. Any questions from anyone? Yes.
Students have a question there. Can you play the rhythm bot?
What's that?
Can you show us the rhythm bot?
It'll take me a minute to find the video. Oh, I guess I could go online.
Website.
I could go to the website, yeah. You're going to hear me talking now. Okay. Yeah, when I show it, you really have to be there because it's like it's about inviting the audience into the space, so to sit and walk around. The robots are responsive to human behavior. We explore ambiguity and agency. So whether you're affecting them or whether they're directing what happens, what we did in May with the lights and sound, we call it a sensitive improvisational environment because it really is exactly what I've been talking about. It's a, you know, we can explore how it responds to unfortunately, you're going to hear me talking. Or maybe you won't. Oh, yeah, here's the mechanism. We have 3 linear actuators connected with springs, so we get all these beautiful resonances. I wanted it to be muscle-like, and they're pendulous, so they're okay, so you can just look at me. I don't have to hear me. Sorry. Yeah, we actually have a video. It just would take me a little while to find it because it was accepted as an artwork to NeurIPS. They have a creative AI track. I mean, it's not really AI in that sense, but it is this kind of artificial collective intelligence, right? And the light and the sound, so Dan Truman, who's just a magnificent composer, there's Dan, he mic'd the bots, because the stepper motors on these 3 actuators make these, just this great sound. And so he's trying not to, one of the things we're trying to understand is called rhythmic entrainment. So it's pretty well understood in the world of music, right? So our brainwaves actually apparently synchronize with the rhythm, and it makes you feel really good. And so the questions that we had, and I studied this with a choreographer, so there was a piece called Rhythm Bath. We were trying to understand if visual cues, so movement, could do that too. And then we were doing it with dancers, and then I asked the question, could we do this with something inanimate? So I started working with, or talking with Sabine Kastner, who's a neuroscientist who studies oscillations in the brain, and she said, I don't know, but you got to try it. So, so we've been, and it's kind of incredible. If you sit there, you just feel really good. And it was kind of an amazing thing to do a project with robots. We started this during the pandemic. We had our first exhibition in a little gallery in Philadelphia in 2022, right near the robotics conference, and the art world came and the roboticists came, and we were wearing masks, but it was a way to kind of make people feel good, feel connected. So you can kind of see them doing their thing.
Other questions? Yes.
So I have a question actually about the original movie you showed with the Starlings.
Yeah.
It reminded me of incompressible dynamics. And so you look at that and you ask yourself, well, how does the communication actually take place across this group of birds? So is it the spacing which does this? And for example, is there like a wave propagation across the system so that if the birds on one side start getting close together, there's a signal that propagates across the system and then causes the birds across the entire thing to sort of shift in almost like a compressible wave, or
in principle. I mean, so this group, so there was, so Irena Giardina and Andrea Cavagna, the 2 physicists who I know well, and we collaborated on this, but they did this big project, and they wrote this paper, which showed, what they were trying to understand is like, at least who's paying attention to whom in a network, right? Can they back that out even before they try to understand how information is propagating. And they did this, I mean, this isn't going to necessarily answer your question, but it was a super interesting paper where they defined this notion of topological distance. So they asked this question, and they used this measure of anisotropy. So they looked at like hundreds of snapshots of these birds, and they computed like where was the closest, like literally around the sphere, where was the first closest neighbor? Where was the second closest neighbor? Where was the third closest neighbor? So basically, when you get up to 6 or 7, they're very, they're in particular places. Once you get past 7, it's just random. So they came up with this notion of it's the number of neighbors that plays a role. So their paper showed, and it might just be for these fish, for these birds, individual birds are paying attention to their 6 or 7 closest neighbors, right? So, I mean, I met them right when they were writing this paper, and I asked them, so, like, why, and they thought it had something to do with robustness to uncertainty. I think things happen just so fast. It really isn't like a domino effect. It's not a linear averaging, like I'm showing you here. And so we asked questions like, actually we asked this sort of simple question, actually looked at a linear averaging model with noise and asked the question, was 6 or 7 somehow optimizing the steady state a dispersion about a consensus about, say, which direction to go in. So we can compute that. If you give me like a network structure, I can compute, if it's white noise, I can compute the steady state variance of these guys. So I didn't have to look at trajectories. I just had to know, you give me a snapshot, I say everybody's paying attention to their 1 closest, and I can write down an hour. If everybody's paying attention to their 2 closest, I can write down an hour. Anyway, so we asked those kinds of questions. Super interesting. It could be related to the volume. It turns out these birds, and this could be related to how information passes and like what those waves look like, but they're not big spheres. They're like fluffy pancakes. They're like a couple of birds thick, which they discovered because they put a bunch of cameras up. This is over the train station in Rome between December and February at dusk. But yeah, they'd probably be able to answer that question. Actually, Krishna could answer that question probably better. Krishna Prasad, because he studied this too. Yeah.
Yes, thank you very much for the talk. I have a quick question about scaling. So how does the model that you built scales with the number of agents and the time scales for the reaction? And still this is in relationship with the question from here, where we have like thousands of birds that at some point.
Right.
So in your case, do you have like some kind of monitoring scaling?
Yeah, I mean, so we haven't introduced time delays, all that kind of stuff. So things, yeah, we can look at arbitrarily large. I mean, we are looking, so because we're getting into sort of this neuromorphic story, we're now looking at, instead of having a finite number of options, we're looking at looking at options that are distributed like around the circle. So, instead of, so you can form opinions like an option or a target doesn't have to be just something that I count and know in advance, right? So somebody could come towards me and I could be forming an opinion over this arc on the circle. Yeah, so I mean, maybe we'll understand scaling in that kind of context, but we haven't really run into that yet, but maybe because we're looking at 2 idealized models so far, right? But it's an interesting question, yeah.
Yes.
You opened with examples of animals. I was particularly interested in the bees making the decision about the hives. Have you thought very hard, maybe to track Medusa, to actually try to fit the model to those physical systems? To say, here are the parameters for bees, here's their connectivity, or is that out of the question?
So, I mean, this was absolutely motivated from that, and the first paper we wrote was all about sort of the consensus decision-making informed by that. I mean, the goal was to take a mean field model and try to understand how we could write down as a network model. One of the things I didn't tell you that we tried to recover, I mean, the problem is that there's just that one experiment on the, so it's not like a ton of data, but what we did discover, I must have told it to someone, I don't think I told you in this talk, is that the bifurcation point in the mean field model is inversely related to the average or the absolute value of the quality of the sites. I mean, this is just like everything is just mind-blowing that these bees are doing this. So what does that mean? That means that, and this is something that we tried to kind of, I mean, we're not trying to necessarily fit. Okay, so we did write a paper on political polarization. Again, not trying to fit. So we were trying to, I worked with a couple of political scientists who were trying to understand the asymmetry in the US Congress, so why one party is more polarized than the other. And so we were trying to use this model as this sort of agnostic test bed without putting any bias in the two different groups, and also not having to pick any parameters. So it was all kind of data coming in and data coming out. So in that case, we weren't really fitting. The reviewer did make us kind of sort of show a bunch of parameters so we could kind of get close. But there the idea was to there's like a hypothesis about it being related to self-reinforcement within a party, so like self-discipline, party discipline. Like, I'll give you money if you vote for my bill, versus what they call, what do they call it? Reflective partisanship. So if the other party is becoming more polarized, then I'm going to become more polarized. And so those were two of the hypotheses that we were comparing, and we ended up showing that latter one was too symmetrizing. We couldn't get the asymmetry the way you could with a self-reinforcing. But there was this idea of I don't want to track every individual or every individual bird. I want to understand kind of the principles and the mechanisms and the, but we were able to do things like say, that the mechanism that we understood, which was, this is kind of a long-winded answer, but is this, this is what I learned from the political scientists that, after in a minute, I don't know about today, but after a democratic administration, the voting population moves the other direction, and vice versa. And you can see. So we looked at data from 1959 to 2019, and you can see these oscillations, but nobody ever really took the time to understand that it's not all equal. It's not a sine wave, right? So you've got larger magnitude and longer periods in one direction or the other. So we use that as the input. And we used that to tune, like in the case of the self-reinforcing, the gain in front of that, and in the reflective partisanship, the gain in front of the interagent. And then the output was this, these opinions. So, that's a long-winded answer. So that's one example where we did that. And we were able to draw conclusions. Depressing ones, but. Yeah.
In these swarms, each of these birds, these starlings, or if you have fish, they're not indistinguishable. You talked about indistinguishable.
Yeah, they're not indistinguishable.
They're
It's
not.
a lot of heterogeneity
There's
that,
a lot of
yeah.
heterogeneity,
yeah.
right?
Which is a super interesting question, yeah.
Yes, and so particularly age distributions
Yep,
in swarms
Yep.
may make some very interesting differences as to
yep,
what age the birds are and how they're distributed in the swarms.
Absolutely.
I'm really curious about.
Yeah,
all
no,
these
it's not
other-
even just age, it's,
Yeah,
they have personalities, so some might be bold and some might be shy. There can be state dependent, like some might be sated and some might not be, you know?
so these are all heterogeneous.
They are.
systems,
So look,
which
we're just
are
scratching the
somehow
surface,
behaving
yeah.
in this astonishingly coordinated way.
It's kind of incredible. Yeah, that's why we add a little bit of, you know, but we're only scratching the surface, adding a little bit of variability, you know, across all these, like all those parameters are all different in this model.
But what strikes me is that in reality, in nature, it's tremendous variability.
Yeah, but I think what the interesting questions are like, when does variability and heterogeneity, and these are, you know, people are thinking hard about this, when it's helpful, right? When it can really
Yes.
make a difference for all these kinds of challenges that these systems and these complex environments have to manage.
Thank you very much. I
Thanks.
think we have.
Thank you.